Hello everybody, welcome to the last lecture on first module of Applied Electromagnetic Theory. Myself, Shama Srikumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. The topics covered in this lecture will be the magnetic scalar and vector potential, Poisson's law for magnetostatics, the Maxwell's equation for time-varying fields, which includes the Faraday's law and the modified Ambience law, and we'll be studying the relation between scalar and vector potential. So we have already discussed about potential in electrostatics. Now we'll see the potential in magnetostatics. So there is a scalar potential as well as a vector potential. So to define the scalar potential, we are taking the help of the vector identity given by del cross del V equal to 0. That is, the curl of gradient of any scalar is always equal to 0. Now, when you consider the Ambience law, the closed integral h dot dl was equal to I and the point form was given by del cross h equal to j. Now, if you compare the two equations, we will get this h to be the gradient of a scalar if j equal to 0. So, we can conclude that h equal to minus del Vm if j equal to 0. Here m subscript denotes it is for magnetostatics. And this Vm is called as the magnetic scalar potential and it is measured in amperes because H is measured in ampere per meter, and here when you consider the derivative there will be a meter inverse, so hence the magnetic scalar potential will be measured in meters. Next we'll be discussing about the magnetic vector potential. So, according to another identity for the vectors, the divergence of curl for any vector A is always equal to 0. That is, del dot del cross A is equal to 0. Now, when you consider the Maxwell's equation, that is a Gauss law for magnetostatics, we already told that del dot B is equal to 0. That is, the magnetic field lines around the closed surface is always equal to 0. Now, when you compare the above two equations, we will get B is equal to del cross A. That is, magnetic flux density can be expressed as the curl of a vector A. And this vector A is called as the magnetic vector potential. And it is measured in Weber per meter. Since B is measured in Weber per meter square, this A will be measured in Weber per meter. Now, when you consider the total flux, we already told psi is integral S B dot ds. This B can be expressed in terms of magnetic vector potential. So, psi can be written as integral S into del cross A dot ds. Consider the Poisson's equations for magnetostatics. So, we have already defined the scalar potential and vector potential. So, we know that according to scalar potential, H equal to minus del Vm if the current density J equal to 0. Now, according to Ambient's law, del cross H was equal to J, but to satisfy the scalar potential, J will be equal to 0. So, del cross H will be equal to 0. Now, what is this H? H equal to minus del Vm. So, on substituting that, del cross minus del Vm equal to 0. So, the curl of gradient can be expressed as del square, the Laplacian operator. So we'll get del square Vm is equal to 0. So this is similar as the Laplace equation for electrostatics. Here instead of the electric potential, we are having the magnetic scalar potential. Now considering the Maxwell's equation del dot B equal to 0, that is it is a Gauss law for magnetostatics. And according to Ambience law, you know del cross H equal to J. Now, when you consider this equation and we multiply both sides by mu, you will get del cross mu h equal to mu into j. Now, what is mu into h? It is b. So, del cross b equal to mu into j. Now, when you consider b, it can be expressed as del cross a. So del cross A equal to mu into J. Now the curl of a vector can be expressed as del into del dot A minus del square A, and that is equal to mu into J. When you consider the divergence of the vector quantity, that is, it is magnetic vector potential and it is a static quantity, the divergence of that will be equal to 0. Similar to del dot B equal to 0, this del dot A will be also equal to 0 for magnetostatics. So on substituting that, you will get del square A equal to mu J, and this is the Poisson's equation which is satisfied by the magnetic vector potential. So the magnetic scalar and vector potential also satisfies the Poisson's or Laplace equation. Now we'll compare what we have studied in electrostatics and magnetostatics. So we started with the basic laws in electrostatics as the Coulomb's law, that is F equal to K Q1 Q2 by R square into AR cap. And the corresponding basic law in magnetostatic was the Biot-Savart's law, which will be determined H given by dH is equal to mu 0 I dl cross AR cap by 4 pi R square. The second basic law in electrostatics was given by closed integral S d dot ds is equal to charge enclosed. That is, the total electric flux crossing a closed surface will be equal to the charge enclosed. And the corresponding magnetic equivalent law was the Ambience circuit law, which was given by closed integral H dot dl is equal to the current enclosed. Now, the electric flux density D, it is given by epsilon E, where E is the electric field intensity measured in volt per meter and flux density is measured in coulomb per meter square. And corresponding magnetic equivalent is given by B equal to mu into H, where H is measured in ampere per meter and B is measured in Weber per meter square. Now, when you consider the electric flux, it is given by the flux density into area, and the magnetic flux is given by magnetic flux density into area. Now, when you consider electrostatics, the flux crossing will be equal to charge enclosed, and it is related to capacitance as equal to C into V. Now, when you consider magnetostatics, the flux is proportional to the current, and the proportionality constant was given by inductance. Now, in the case of capacitance, the current is given by I equal to C into dV by dt, and in the case of inductance, V is equal to L di by dt. Now, when you consider the electrostatic energy density measured in joules per meter cube, it was given by half d dot E. For the magnetostatic energy density, V will be replaced by B and E is replaced by H. So it is half B dot H. And we have learned potential in electric statics as well as magnetostatics. So E was equal to minus del V in the case of electrostatics. Whereas in magnetostatics, E will be replaced by H and V is the magnetic scalar potential. And this will be satisfied only if the current density J equal to 0. So now we'll consolidate the four Maxwell equations for static, electric and magnetic fields. The first equation was the Gauss's law, which was in the form del dot D equal to rho V. It is the point form or differential form, and the corresponding integral form is given by closed integral S d dot ds is equal to integral over volume rho V dV. So this is the divergence of electric flux density. So we'll write second equation as the divergence of magnetic flux density. So we got it as del dot D equal to 0. When we convert it into integral form, you will get it as closed integral as B dot ds is equal to 0. And this equation implied that we don't have magnetic monopoles. That is, the magnetic poles north and south always exist in pairs. Also, the property to be noted is that the magnetic field lines are always closed. Thus, when you consider a closed surface, the net magnetic flux lines crossing it will be equal to 0. Now, these two were the properties which divergence of electric field flux density and magnetic flux density. Next is the curl of electric field intensity. So when you consider the curl of electric field intensity, it is equal to 0. And when you convert it into integral form, it will be closed integral L E dot dl equal to 0. And this gave us the conservative nature of electrostatic field. That is, the work done in taking the charge around the closed path will be independent of the path followed. So, if the electric field intensity satisfies this equation, then it's said to be conservative. And the fourth Maxwell's equation was the Ambience law, and it was given by del cross H equal to J, which is equal to closed integral L H dot dl, which is equal to integral over S J dot ds. Now, till this point, we have derived the Maxwell's equation for static fields. Now, we'll be extending that concept onto time varying fields. So, when you consider static electromagnetics, the electric field and magnetic field are independent quantities and they are not dependent on time. And that both electric and magnetic field will be present separately. But when you consider dynamic electromagnetics, both electric and magnetic field will be dependent on one another. And when you consider the time varying fields, it will be dependent on the third parameter, which is time. Earlier, when you consider electric and magnetic field, it was just a function of the coordinates x, y, z. Here, it is also a function of time. Now, when you consider stationary charges, it produced what was called as the electrostatic fields. And when the charges move with a constant speed, we got current, and that current produced the magnetostatic fields. And when this current was varying with respect to time, we will get what was called as the electromagnetic field or wave that was produced due to the time varying current. And in turn, it produces electric and magnetic field which are dependent on each other. So to derive the Maxwell's equations for time varying fields, we'll be first discussing about Faraday's law. So according to Faraday, when you consider a static magnetic field, there will be no current. That is, you should have a time varying field. This time varying field will produce an induced voltage, and that is called as the electromotive force or EMF, and this will produce the current flow. And when you consider the induced EMF in a closed circuit, it is equal to the time rate of change of flux linkage by the circuit. That is, V EMF will be equal to minus d lambda by dt, where lambda is the flux linkage. When you consider the psi, which is the magnetic flux, this lambda will be equal to n into psi. That is where n is the number of turns present and flux psi is the flux linked to each turn. So lambda is replaced by n psi, so it is minus n d psi by dt. Now this lambda equal to n psi is called as the flux linkage. Now when you consider here, there is a negative sign. This means that the voltage will be in a direction such that it will oppose the flux producing it. That is, flux is produced, then the voltage induced will be in the opposite direction. That is why we are having a negative sign, and this is proposed by Lenz's law. That is why V EMF is expressed as minus N d psi by dt. The potential can be written in terms of electric field intensity as the integral of E dot dl. So here we are considering a closed circuit. So the EMF can be written as closed integral L E dot dl. Now when you consider the flux psi, it is the integral over surface B dot ds. That is the flux crossing unit area. So it's flux density into the area. Now, when you consider this surface S, this is surface which is formed by the closed path L. So, this is an open surface which is formed by the closed path L. Now, when you consider the Faraday's law, which we told earlier, V EMF is minus d psi by dt, where we are taking the number of turns to be 1. Now, substituting the expression for psi into this expression, we will get it as minus d by dt integral over s b dot ds. This is the expression for V EMF. Now, when we consider this d by dt and the integral, if you want to exchange the integration and the derivative symbol, we'll take this d by dt inside. But when you consider the flux density B, it is a function of more than one variable. That is, it depends on the dimensions as well as time, etc. So when you take d by dt inside the integral, it changes to dou by dou t, that is partial derivative. Hence, V EMF changes to minus integral as dou b by dou t dot ds. This is the induced EMF in a closed circuit. Now, on comparing the two expressions for EMF, we will get VEMF is equal to closed integral L E dot dl, which is equal to minus integral over S dou B by dou T dot ds. So, when you consider the LHS, this side is having electric field intensity and the right hand side is having magnetic field intensity. This means that both electric field intensity and magnetic field intensity are dependent when you are considering a time varying field. So when you consider the LHS, it is closed integral L. So according to Stokes' theorem, we know that the closed integral over a path can be equated to the surface integral of the curl of the field. So this closed integral L E dot dl can be equated to integral over S del cross E dot ds. That is, this integral is replaced with the surface integral of curl of the field. Now substituting this back into this expression, we will get it as del cross E is equal to minus dou B by dou T. That is, when you compare the above two equations, we will get that del cross E equal to minus dou B by dou T. That is, if you are having a time varying magnetic field, it will produce an electric field. This is the implication of Faraday's law. So to form an electromagnetic wave, we require both an electric field as well as a magnetic field which is time varying. One of the Maxwell's equation for time varying fields is given by del cross E equal to minus dou B by dou T, which is different from the Maxwell's equation for static field, which is given by del cross E equal to 0. We got del cross E as 0 for a static field because there is no dependence on time for a static field. So the rate of change of field with respect to time will be 0. So this equation also implies that for a time varying field, it will not be conservative because we don't have the value of del cross E to be 0. If del cross E is 0, then only we can tell that it is conservative. So if it was a conservative field, the work done in moving around the closed path will be equal to 0. But here what is happening is that if you are taking the charge around a closed path, a time varying field, electric field is produced due to a time varying magnetic field. So electric field and magnetic field are interdependent. The next concept which we need to discuss is about displacement current. So to discuss about displacement current, we will consider the Maxwell's equation for curl of the magnetic field given by del cross H equal to J, which was the Ambience law. Now we are applying the divergence operator either side of the equation. So we will get it as del dot del cross H is equal to del dot J. But according to the properties of vector identities, the divergence of curl of any vector is always equal to 0. So we know that del dot del cross H is divergence of curl, which is equal to 0, and that will be equal to del dot J. But we already know that according to continuity equation, del dot J is equal to minus dou rho v by dou t, and this value will not be equal to 0. So according to continuity equation, del dot J is always not equal to 0. So when you compare equation 2 and 3, it turns out to be invalid, or there seems to be some contradiction between the two statements. That is, we'll get del dot j 0 in one case and non-zero in the other case. So we need to develop an equation so as to remove this contradiction in the expression for del dot j. This led to the development of the term displacement current. So to remove the contradiction, we are modifying the equation as del cross H is equal to J plus JD. We have introduced an additional term JD. Now we are applying the divergence operator on either side of this equation. So we will get it as del dot del cross H. We know that the divergence of curl of the vector is 0. So this is equal to 0, which is equal to del dot J plus del dot JD. Now, according to continuity equation, del dot J is equal to minus dou rho v by dou t. Substituting this into this expression, we will get del dot JD is equal to dou rho v by dou t. So, del dot JD by JD is the new term which we introduced into the expression. Now, according to Gauss's law, we know that del dot D equal to rho v. Substituting it into the above expression, we will get del dot jd is equal to dou by dou t of del dot d. Now, when you take the divergence operator outside, we will get del dot jd is equal to del dot dou d by dou t. Thus, from the equation del dot jd is equal to del dot dou t by dou t, we will get the value of jd to be dou d by dou t. So, the new term which we introduced into the expression is given by jd, which is equal to dou d by dou t, which is a rate of change of electric flux density. So when you substitute back into the curl of the magnetic field intensity, we will get del cross H equal to J plus dou D by dou T, and this is called as the modified Ambience law, and this is the expression for Maxwell's equation for time varying field. From this equation, we understand that if we are having a time varying electric field, it will produce a magnetic field. From this equation also it is clear that both electric field and magnetic field are dependent for time varying fields. So when you consider the term JD, which is equal to dou D by dou T, it is called as the displacement current density. And it is the additional term introduced to the equation del cross H equal to J. And the other term J, which is already present in the Ambience law, is given by sigma E, and it is called as the conduction current density. So if we are having time varying fields, then it will have both conduction current as well as displacement current. So the insertion of the term JD, which is the displacement current density, into the Maxwell's equation, that was the major contribution by Maxwell. That is, without the term JD, then the propagation of electromagnetic waves will not be possible, since it led to the contradiction with the continuity equation. So if you know the value of displacement current density, then you can find what's called as a displacement current by multiplying it with area. As you all know, current density is current per unit area. So if you multiply the displacement current density with the area, we will get what is called as the displacement current. Now the value of displacement current density was equal to dou d by dou t. So substituting back jd equal to dou d by dou t, we will get it as integral as dou d by dou t dot ds, and which is the value of displacement current. So we have learned two terms, magnetic scalar potential and magnetic vector potential. We'll try to derive a relation between the scalar and vector potential. So we know that the magnetic vector potential is given by B equal to del cross. Also, when you consider the Faraday's law, it was given by del cross E equal to minus dou B by dou T. So, when you consider the expression for B, we can substitute it as del cross A. Substituting equation 1 into 2, we will get del cross E is equal to minus dou by dou T of del cross A. Taking the operator del cross outside, we will get del cross E plus dou A by dou T equal to 0. So we have taken this minus dou by dou T del cross A into the LHS, and we have modified the equation into this form. Also, we know that for scalar magnetic potential, del cross minus del Vm is equal to 0 if J equal to 0. That is, if the current density J is 0, then the scalar magnetic potential was defined. So, when you compare these two expressions, you will get E plus dou A by dou T equal to minus del Vm. Hence, the electric field intensity E equal to minus del Vm minus dou A by dou T. So, this gives the relation between electric field intensity, magnetic vector potential, and magnetic scalar potential. So now we'll conclude for the Maxwell's equations for time varying fields. So when you consider the divergence equations, both the equation remains the same. So the first Maxwell's equation was given by del dot D equal to rho V, which was the point form of Gauss's law, and its integral form is given by closed integral S d dot ds is equal to integral over volume rho V dV. So this was the Gauss's law. The second Maxwell's equation, which was for the magnetic field intensity's divergence, it was given by del dot D equal to 0. Converting it into the integral form, we will get closed integral as d dot ds is equal to 0. And from this equation, we already implied that there will not be any magnetic monopoles. Poles always exist in pair and the magnetic field lines are always closed. That was the implication regarding this equation. Now, the third and fourth equation got modified in the case of time varying fields, where the third equation was the Faraday's law, where del cross E equal to minus dou B by dou T, which was the point form or differential form. And when you convert it into the integral form, you will get it as closed integral L E dot dl is equal to minus dou by dou T of integral over S B dot ds. So this implied that if we are having a time varying magnetic field, it will produce an electric field. And the last Maxwell's equation was modified from the Ambience law, and it stated del cross H equal to J plus dou D by dou T. Now, when you converted it into integral form, we got it as closed integral L H dot dl is equal to integral over S J plus dou D by dou T dot ds. And this was the modified Ambience law. So when you see this equation, if you are having a time varying electric field, it will produce a magnetic field. So these two equations led to the propagation of electromagnetic waves, and it will be produced only if we are having a time varying electric field and a time varying magnetic field. With this, we come to the end of the first module of Applied Electromagnetic Theory. In this module, we discussed the different concepts in electrostatics and magnetostatics, starting from Coulomb's law, Gauss's law, Ambience law. Then we studied the energy density for electrostatics and magnetostatic. Then we extended the Maxwell's equation for time varying fields like Faraday's law and the modified Ambience law. Also, we studied the boundary conditions for electric and magnetic fields and the potential, electric potential and magnetic potential. and also the Poisson's and Laplace equation in electrostatics as well as magnetostatics. Thank you.